In this video, we're going to review the theory of relays. All right, our objectives for today are to give the definition of a relay. We'll review key terms that are used with relays, and then we'll go over the theory of operation for a relay. The first thing that we're going to talk about is an electromechanical relay. There's different types of relays. The first one that we'll look at is electromechanical. An electromechanical relay has an electromagnet. So this is the key piece of a electromechanical relay. There's lots of different types of relays. All electrical mechanical relays are relays, but not all relays are electromechanical relays. In order for it to be a relay, it needs to operate as a switch that is turned on by another circuit. So in short, relays are switches that open and close circuits electromechanically or electronically. So a lot of times what we would talk about is switches before we talk about relays. And so if I have a switch here that I'm using to turn on a light bulb, this would be a switch. Electromechanical relays are switches. They have the ability to open and close the circuits, but they're not operated by hand. They're operated with an electromagnet. So the relay turns on a load circuit, on or off, by energizing an electromagnet, which opens or closes contacts in the circuit. So when we get into electromechanical relays, the key thing that we're going to talk about quite a bit is that there's two circuits. There's a circuit that handles the switching, and then there's another circuit which handles the electromagnet circuit. And so there's two circuits in an electromechanical relay or in any type of relay. One to actually do the switching, and then there'll be another circuit that's going to control the electromagnet. All right, so our key terms, the first thing that we're going to talk about is the coil. So the coil is the electromagnet circuit. The coil would either be shown as an inductor symbol. That's not very good. Let's try that again. So we'd have the inductor symbol for a coil, or we would show a coil like this. In electronics, a lot of times we show this schematic or this symbol. If we were working in an industrial setting, this would be our coil. The contacts are either shown, there's a couple different ways to show them. We could show them as normally open. We'll talk about what that means in a little bit more detail later. They could be normally closed. And so these contacts are used for the second circuit. So the first circuit controls the electromagnet, and the second circuit is the contacts. So in a simple relay circuit, you might have, let's say, like a 1.5 volt battery that's energizing a coil, and then on here, let's say that we have a switch. So here we have a switch, and then we have a relay coil and a contact. This is how they would be drawn in multisim. And then let's say that this is a light. And let's say that this is, actually I'm missing some things here. So let's say that this is our contact, and then we have a AC source. So here is a light bulb, and then we have a 120 volt AC supply. So what's happening in this schematic is we have a battery that's connected to a switch. This would be our relay. When we energize the relay coil, the contacts close and it turns on the light. We'll look at some more examples of that. The contacts, these are the contacts here, and the coil is here. Try to draw that a little bit better. When we have contacts, there's a couple of things that we're going to go over. There's poles and throws. So a pole is how many circuits can we control? And we'll go over a couple examples of that. Down here we talk about the different types. And the throws are the connections. These are the connections or the positions of a switch. So let's look at this first one. This is this one would be called a single pole, single throw switch. So this would be a switch or a contact that has basically just two connection parts. It can be connected here and here, and it can only break one circuit. So this switch here would be a single pole, single throw switch. This is like a home light switch, a very simple switch. There's only two screws. If we were drawing it as a relay contact, it would look like this. This would be a single pole, single throw switch. So it can break one circuit, and it only has one position on the circuit. The next one we'll look at is a single pole double throw. So this one looks like this. And in this circuit, there's two positions for the contacts to land. And so on here, there's 1, 2, 3 connection pieces. This one would be called the common pin, and then it can either be connected, this can go back and forth, it could either be connected to A or B. So this one has two throws. This one is a single pole. This stands for double throw. So it's a single pole double throw switch. And this has two throws, which means it has two positions that this contact here, this little armature, can either be connected to A or B. It's kind of like a train. You know, if you want to make if you think of the current as like a train, it comes in, and you can either go to B or it could go to A. If we were drawing this in terms of contacts, it would look like this. A lot of times, this is the type of contact that we would see on a electromechanical relay. I can draw it a little bit better here. And just like the other one, what we would have here is a common. And then we would have, this one would be called the normally open, and this would be called the normally closed. So there's 3 pins on this single pole double throw contact, common, normally open, and normally closed. Next type of switch that we'll be looking at is a double pole, single throw. So this one has 2 sets of contacts, and a lot of times this one we would draw like this. And so there's 2 poles. So we have this circuit, let's call this circuit 1 and circuit 2, that'll both be connected. And then a lot of times we'll show this with a dotted line here between the 2 contacts, which means the contacts here move together. And so this would be the type of switch that you would use for a 240 volt circuit, and you'd have two separate contacts, so you could connect two hot wires to this. This one, if we were looking at the contacts on a relay, this would look like this. We would use this. This would be a 2-pole contactor. The last one that we'll look at is a double pole, double throw switch. So now we have two sets of contacts, and now they're both normally open, normally closed. So this would be, I'll draw this one up here. This would be like this for a relay. So we'd have one set of contacts, normally open, normally closed. Then we'd have another set of contacts, normally open, normally closed. And so if we looked at the pins, or where we would connect wires, we'd have screws here for the double pole single throw, and then for this one we would have wires like this. And this is the type of relay contacts that we're going to see when we get to our 8-pin relays later. They'll have two sets of contacts, both with a normally open and a normally closed setup. All right, so here is a kind of a cutout of the electromechanical relay. We'll notice that first we have electromagnet, and so the electromagnet is going to have a voltage that requires the electromagnet to be energized. It's going to require a certain amount of energy so that the magnet is strong enough to pull the armature to close the contacts. When we're dealing with electromagnets, what we care about is the voltage, and these come in all different sizes and shapes, and voltage levels could be 5 volts, 12 volts, 24 volts, 120 volts, 240 volts are all available, and they could be AC or DC. The rating on the electromagnet, the design of the electromagnet will be determined based on what they specify for the voltage. And so depending on the application, all of these different voltages would be appropriate. So the next part is the armature, and these are the contacts. The contacts, that part is the what we would call the high power circuit. The electromagnet is the low power circuit. And the contacts are rated based on current mainly. So we're worried about how much current could we handle for the contacts, and these will be all over the place, anywhere from something like 10 amps all the way up to 400 amps, depending on the type of relay. All right, so when the coil is energized, that means when we're energized, this means that the magnet is on. So when the electromagnet is on, this armature is going to pull forward, and the normally open contacts will close. So when the coil is energized, the core becomes magnetized and attracts the iron arm of the armature to it. As a result, the contacts on the armature close. When we say the contacts close, this means the normally open contacts, the normally closed contacts will open. When the coil is de-energized, the armature returns to its normal position and the contacts on the armature open. The coil and contacts are insulated from each other, so no circuit will exist between them. Notice that there's no electrical connection between the low power circuit and the high power circuit in an electromechanical relay. All right, so let's look at an example here. So let's say that we have our battery and we have a switch, and then we have a relay coil. So we're going to call this CR1. So this CR1 is nomenclature that we use in industrial electricity. This means control relay 1. And let's say that we have another circuit. So let's say that this circuit is a 5-volt circuit. And let's say that we have another circuit, and let's make this one an AC circuit, 120 volts. And we're going to use a normally open contact for CR1. And that's going to turn on a light bulb. Okay, so this is my light. And let's say that the light is a 120 watt light, which would mean that there'd be 1 amp of current coming from the supply in order to power the light. So we'd have 120 volts and 1 amp. All right, so let's look at this in terms of states. So we're going to kind of draw this in 2 states. So the first state, let's say that we close the switch. So we'll say state 1, we're going to close the switch. So that means that if we were to draw this again, somebody actuates the switch. So this is closed. So now our CR1 is energized. So this means that the electromagnet is on, the coil is energized. If we had a 5-volt supply, that means that we would have 5 volts across the coil and the electromagnet would turn on. In this scenario, we would have 0 volts across the switch, and the Kirchhoff's voltage law would still apply at 5 volts equals 0 plus 5. Now, for the contact circuit, so we have 2 circuits, we have the coil circuit and the contact circuit. What will happen is that our normally open contact will close. So this is a normally open contact that's showing that it closed. And sometimes we show that in a different color. So let's show that in a different color. So these contacts we're saying are closed, which means that current would flow between them. And so this means that on our light circuit, we have 120 volts. This is closed, so we'd have 0 volts across the switch, and we would have 120 volts across our light, which means that our light would be in the on state. So we would have 1 amp of current flowing. The current in this circuit would be dependent on the coil. Usually this would be somewhere around like a 1/2 amp or something like that. So it's not a lot of current, maybe a 1/2 amp or something like that to energize the coil, or less, depending on how big this electromagnet is. All right, so let's go to the next states. Let's say somebody opens the switch. So now we're at state 2, and we open the switch. Let's look and see what happens. So here we'll draw this again, this time with an open switch, and we have the relay coil, a 5-volt supply. This is open. This would be CR1. And then we have our high power circuit over here, 120 volts. This is CR1. This is our light. Okay, so now the switch is open. So that means when we have an open switch, we'd actually see 5 volts across the switch. We would get 0 volts across our relay. Kirchhoff's voltage law always needs to apply. It's a law. So when we have an open switch, we get 5 volts across it. And we get 0 volts across our relay. This means that this is de-energized. Over in this circuit, this is a normally open contact, and it's in its open state. So when this is open, that means that we would have 120 volts across the contacts of the relay. And we'd get 0 volts across our light, and the light would be off. So these are the two states that our relay can operate in. It can be energized, and when we're energized, the normally open contacts, let me draw that differently. So when we're in the energized state, the normally open contacts are going to close. Like this would be closed. And when we're in the de-energized state of the electromagnet is de-energized, the normally open contacts are going to be open. Now, if we had normally closed contacts, let's say that we had some other circuit that was using the normally closed contact. So let's say that we have a circuit here and it's using the normally closed contacts. This is going to operate the opposite way. Let's say that this is CR1. So for this one, it's normally closed. So if we had a normally closed contact, what we're going to have is that this is going to open. And so, it's kind of hard to draw, but we would show it as open. And then when the coil is de-energized, the normally closed contacts would be closed. And so I'm going to draw this kind of like a dotted line. I don't know what the best way to, this is kind of hard to draw, but it's a normally closed contacts. Now, usually when we draw schematics, we only show the contacts in their normal state, either a normally open or normally closed. And so then it's up to the person interpreting the schematic to understand how it's going to operate. All right, so here is another example of electromechanical relay, maybe with a little bit better picture. Here we have a voltage supply. Let's say that it's 10 volts, just so that way we have some sort of reference. And then let's say that this time we have 200 volts AC. So the first thing that we want to always remember is that there's two states with an electromechanical relay. There's the control circuit, and then there's the load circuit. And they operate on different voltages, and there's different wires, different wire sizing, all of that. And so when we close the switch, this is our switch here, just like we had before. With the switches open, the coil is de-energized. So when the switch is open, the coil is de-energized. This would be our state 1. The normally open contacts are open. The normally closed contacts are closed. If we go to state 2, where we close the switch, so we have switch is closed, the coil would then energize, and the normally open contacts would close, and the normally closed contacts would open. So when we energize this coil, the open contacts close and the closed contacts will open. Here's another example of a way to show the schematic. This is with what we call a ladder diagram. So in a ladder diagram, we have our positive and our negative over here. And so they're showing two relays. This is the symbol for a push button. And when we push the button, we would energize the coil, and then the normally open contacts would close. Now, up here, they're going to talk about some different symbols. A letter is used in most diagrams to designate the coil. M means that it would start a motor. So what we're looking at is how are these contacts connected? Are they connected to a motor? So that would look like this. So maybe we have a motor here, and our contacts are connected to a motor, so we decided to call this M or M1 or MS1. So this would be motor starter is what MS stands for. And all of the coils usually will have their own unique name. They'll be labeled in the panel with the name. CR stands for control relays. So you hear control relay 1, control relay 2. So that depends on the application what we call the coil. The other one that you'll see sometime is CT. CT stands for contactor, and a contactor is basically just a big relay. So it's a relay, it has the same parts, but it's designed for more current. And so we'd use these to turn on things that are running at higher voltage, higher power, things like industrial motors, industrial heaters, HVAC systems, compressors, things like that. All right, so here's another example of an application. This time they're showing it kind of like a inside circuit and an outside circuit. Here we have a 480 volt circuit. 480 volts is common in manufacturing or industrial settings. We don't do very much with 480 in our classes because we're worried about students getting electrocuted. In factories, the reason why they go with 480 volts is because you can get the same amount of power with smaller wires. And so that's kind of the standard voltage inside factories. So here we have a load. This could be a, that's not really specified, but this could be like a large motor or something like that. And here we have a relay, and we have the coil is rated for 12 volts. And depending on how much current is flowing, that would determine how big the relay's contacts would need to be. So here we're showing a relay where we're doing power amplification. We have a low power circuit. So this one is low power. It's just energizing the coil. And then we have a high power circuit here. And so we could use something that's low energy and turn it on something that's very high energy. Here's another example of a relay application. Here we have a sensor which has a very low signal current. So this is a low power device, and it's going to go to a transistor. Now we haven't talked about transistors too much in this class, but transistors are what we would call a solid state relay. Now, solid state is a term that you may have heard before, things like a solid state hard drive. It means that there's, it's a solid piece, so there's no moving parts. Some of you may remember hard drives used to spin. They used to have a motor on them and they would spin. And when they came up with solid state hard drives, there was no moving parts, and that was a big advantage. Solid state relays have some advantages. They're faster, and they draw less. They require less power to turn them on. So there's no electromagnet. So inside a solid state relay, there's no magnet that needs to turn on. Now in this circuit, this is a power amplification circuit. So we have a sensor that's connected to a transistor. And then the transistor is going to be connected to the coil of electromechanical relay. So the sensor itself doesn't have enough power to energize the coil, even though the coil is a pretty low power circuit. And so they're using a transistor to amplify the current from 2 milliamps to 20 milliamps. In this case, the 20 milliamps is enough to energize this coil in this electromechanical relay, which then is connected to a contact that can turn on a solenoid valve, which draws 2 amps. So we're going from 2 milliamps to 20 milliamps to 2 amps. So this is kind of showing power amplification using 2 relays. Every time we amplify the power, we need some sort of relay. So we have our transistor that acts as a relay, and then we have our electromagnet that acts as a relay. Relays have different pins and styles, so we want to go over how we read the schematic. So here's our electrical schematic that we would see. This is on the cover actually of most of these relays. So when we're looking at our schematic, there's two parts. There's the coil and then the contacts. So let's look at the coil first. So we're always looking for the coil first. So the coil's pins are here on this. This is a standard convention. The coil, the pins that we're going to use for the coil are 2 and 7. So on this relay, there would be these are plugged into relay bases, and on the relay base, there's a bunch of screws. And so when we attach our wires, what we're looking for is what pin do we connect them to. So these on the base next to the screw, there'd be like a 8, 7, 6, 5, 4, 3, 2, 1. We'd actually see these pin numbers on the base. And so when we go to our circuit and we're trying to connect our circuit, that would be what wire we would connect to be on the coil, is 2 and 7. So like if this was our circuit, we would connect a wire from the switch to pin 2, and then we would connect pin 7 back to the negative on the supply. Now the contacts, they're a little bit differently. There's this relay is an 8-pin relay, so it has 8 pins. It has 2 poles, so it's a 2-pole relay. So if we look on here, this is the poles. This would be the first one here. And on our contacts, we have a common terminal. So pin 1 here is the common. And then there's a normally open and a normally closed. So if we look here, pin 1 is the common. And then that comes up here and it's connected to pin 4. So pin 4 is the normally closed. And pin 3, which is here, what this is trying to show is that this could go from this position to this position if the coil was energized. So pin 3 is our normally open contact. The next set of contacts is over here. So if we look at these, this would be 8, 5, and 6. These are all connected together. And so 8 is the common. And then the normally open, if we go here, we're coming up 8. This would be connected like this when this armature is going to move here. So 6 is normally open and 5 is normally closed. Oops. Okay, so that's how we would read a schematic. We do have in class, we do have 11-pin relays, and they're what we call 3-pole relays. So there'd be a third circuit on here, and we use those quite frequently in the lab. All right, so this is another example of the contact specifications. We talked about these earlier. We have single pole or double pole, and it's showing that these two are mechanically connected. That's what this dotted line means, that these are connected mechanically. So if one opens, the other one opens. The pole is the number of switches in the contact set. So how many switches, a lot of times I'll talk about this as the number of circuits. So if we have a single pole, we can do 1 circuit. If we have a double pole, we could do 1, 2 circuits. The throw is the number of positions. So is it going between just 1 position, or is it going between 2 positions? So in a single throw, we have a common, and then we have one output. In a double throw, we have a common, and then we have a 1 or a 2, or we could say maybe A or B, depending on how we wanted to describe it. Breaks. Breaks are the number of points which the current will be interrupted. In bigger relays, we'll see a double break. This would be for high current applications. A single break would be for low current. Usually if we're, 15 amps or less, a single break is fine. Usually a double break is for 15 amps or more. And that's just kind of my general statement. It's not, depending on the manufacturer, they might have a double break or a single break, but usually the way that I would define it is right around 15 amps is where we would make the decision to go to a double break. If we have a double break, you get less, the reason that we would do the double break is you get less arcing. So when the single break closes, you get a lot of arcing because this side is positive and this side is negative. When you break it in two places, this side is positive, this side is negative, and this is what we call floating. So there's not as much potential there, and if they both hit at the same time, you don't get any arcing. So that's a concern when we have more current. Here's another example of some other circuits. This one includes a 3-pole circuit. So this would be our 8-pin relays are like this. So this would be the 8-pin ice cube relays we have. If we had an 11-pin relay, it would have this specification. This one here, which is a 3-pole single throw relay, this is what we would have on our contactors. So when we get to other classes, when we have our contactors, a lot of times they'll have 3 breaks. 3 poles. It's a single throw, 3-pole contacts, and this is for 3-phase power. So you'd connect line 1, line 2, line 3 here. If you were trying to turn on an air conditioner, so like a AC unit in your house, you would need a double pole single throw switch because if we have 240 volts, we end up with a line 1 and a line 2, both are hot, and so you need to break both of them. That's kind of the standard convention. Some of these other ones we don't use quite as much, but those are the most common, and these are all the different configurations you can buy your relays in. All right, that's it. Thank you.